Hello, good morning, everyone. Today we'll be talking about mechanical behavior of materials. This is a subject for first year MTech student in that second semester. So, myself, Amulya Vihari Patnaik, I'm a faculty member in this Department of Metallurgical and Materials Engineering, Indira Gandhi Institute of Technology, Sarang. So, this will be the assessment in this subject. You have 10 marks for quiz attendance, some assignments, and internal exam you have 30 marks, and final exam 60 marks. So total 100 marks exams. To start with, the subject, the mechanical behavioral materials. So in the part one, we'll be covering the mechanical fundamentals. That is, we'll be introducing you to mechanical metallurgy, and then we'll be talking at looking at stress and strain relationship of elastic behavior, elements of the theory of elasticity. Then after you get a good understanding of the mechanical fundamentals related to stress strain, relationship between stress strain, and theory of elasticity, and all those things will enter into slowly will enter into metallurgical fundamentals, where we'll be talking about very important topics related to metallurgy, or the physical metallurgy. You can talk on and mechanical metallurgy. There is one is your plastic deformation of single crystals. Then the very important dislocation theory, strengthening mechanisms, and fracture. So next is the part three, that is the application part to material testing. So after looking at all those theories involved in mechanical behavior, that is related to dislocation theory, plastic deformation, strengthening mechanisms, and all those things. So we'll be looking at applications to material testing, that is tension test, hardness test, torsion, fracture mechanics, brittle fracture and impact testing, fatigue in materials, creep and stress rupture. So the very very important test for evaluating the service suitability of the material. Okay, so the objectives of this, if you look at why you are going to study this subject, you will be able to know interaction of stress and strain on materials in elastic and plastic manners, and then deformation behavior of the metals due to dislocation interaction, as well as strengthening mechanism of metals, that will be discussing over here. Then we'll be discussing about different methods of testing, the mechanical testing, along with the interpretation of sensible information from the obtained data, such that mechanical assessments are appropriately selected for the required applications. Then we'll be looking at some metallurgical aspects which affect the mechanical properties of materials, and then finally the cause of material failure. That is very very important as far as the industries are concerned. What is the cause of the failure of the component that is being used in the industries? So that you need to investigate to find certain possible solution to eradicate or to mitigate that. So these are some of the references. You can follow some very good books over here that is mentioned. The one and only book, the first one, the first reference you see, that is a mechanical metallurgy. The book by G.E. Dieter is a very exceptional book. It's a kind of a Bible or a Gita for a metallurgist, or you can say it as a mechanical metallurgist. So that is written in SI metric edition by McGraw Hill. Okay, other books you can also follow. Another good book is this to look at the physical metallurgy part. If you want to look at physical metallurgy and materials engineering, then you can refer Small Man, Ari Small Man, and RJ Bischoff, and it is being published by Butterworth and Henman. Okay, and for fracture mechanics, you have Edwards, Van Hill, and St. Rolf, J.M. Bazom. All these things you can follow. These are some of some other books which you can look at. So the question is, why failure in materials? Why actually the materials fail? Okay, so if you see this, this is a very common example of the failure of the Liberty ships. during services in World War II. Okay, so those are used in World War II, and you see the failure that has occurred in the steel in the figure. Seven of the Liberty ships built during the World War II has broken completely in two as a result of brittle fractures. Over 100 of approximately 5,000 merchant ships built during the World War II had developed cracks of considerable size by 1946. You see this failure that has occurred. It's mainly due to the changes happening inside the materials that has been used to make this this ship. So another example, if you see the collapse of Point Pleasant Suspension Bridge in West Virginia on December 15, 1967, the bridge building industries did not pay particular attention to the possibility of brittle failure. Again, this brittle failure. And the failure of Point Pleasant Bridge in 1967, the bridge collapsed without warning, costing 46 lives. This, you see the loss of life and property due to the failure of materials. So another example, the failed fuselage of Aloha 737 aircraft in 1988. The aircraft was used for inland transportation for 19 years before failed. Failure has been attributed to multiple site damage. So you see, to evaluate the material property, okay, to quantify the material properties, you have different tests. First one is, you see, the hardness. Hardness test can be of two types. One is your micro hardness test, another one is your macro hardness test. Then to evaluate properties, material properties like strength and ductility, which is measured in terms of elongation or area of reduction, you have tension tests. Then to evaluate the high temperature, strength, elevated temperature strength, you have creep tests. Then torsion tests. Then you have toughness, that is resistance to failure, impact test, fracture toughness test. Then you have fatigue. You have SN fatigue test, fatigue crack growth test. All those tests are used to evaluate the mechanical properties of the materials. So first one, you see that the hardness test. Okay, hardness, we all know that is a property which is a measure of resistance to permanent sort of deformation or plastic deformation. In the figure, you can see the micro hardness instrument. That is a Vickers micro hardness instruments. You see that there is a indent. Black one is the indent on the surface of the sample. It's a, I think it's a diamond pyramid indenter. So during using different indenters, that is ball, diamond, depending upon the different types of hardness. For example, you have Brinell hardness, Mayer's hardness, Vickers hardness, Rockwell hardness, and all those things. Then you have the tensile strength. Tensile stress, as we all know, that it is carried out in a universal tensile testing machine. So you can see in the figure over here the tensile testing configuration, right? You can see the jaws holding the samples. Then you have a graph, the samples of plate samples. You can see round specimens. You can see. So basic, so it's provide basic design information on the strength of material, acceptance test for the specification of materials. So different parameters which you measure from the tensile stress are the tensile strength, yield stress, Young's modulus velocity, percent elongation, area of reduction. So next is your torsion test. So torsion is nothing but twisting something, twisting the specimen, twisting moment to the specimen and measure the torque. Has not been standardized though, but parameters are shear modulus, torsional yield strength, modulus of rupture. The creep test is the high temperature progressive deformation of material at constant stress. So you see the typical very common creep curve over here, which shows three stages: strain versus time curve, which shows three stages of creep. Initial stage, you have a mid stage, stage 2, and then the final stage is stage 3. Okay, the tensile specimen is loaded at a constant elevated temperature. Strain is measured with time. Parameters are grip strength, grip rate. Then you have impact test. You see the figure. Charpy impact testing is being shown in the figure. So it measures the toughness of materials in terms of energy absorption. Specimen is impacted by a hammer, and the energy absorbed during fracture is measured in joule. It is easy and practical. Establish ductile to brittle transition temperature (dBTT), and not a standard material parameter, should be used in conjunction with other material properties of strength and fracture toughness material parameters. So parameters that you determine from here is the impact energy, ductile to brittle transition temperature. Very, very important, this ductile to brittle transition temperature. Then we have fracture mechanics. So it talks about resistance of materials to crack propagation. Crack propagation can be predicted before failure. Material will fail When the stress intensity factor K, this is the critical. So these all these things we'll discuss as we move on with the subject. And the parameters we have is the fracture toughness K1C, crack tip opening displacement CT, OD, J integral J. Then we have the fatigue stage when there is a cyclic loading. Okay, so material is subjected to a repetitive or a fluctuating stress, that is cyclic loading, and will fail at a stress level much lower than that causes failure in static loading. Okay, so SN fatigue test and fatigue crack growth resistance. So you see that the stresses in fatigue loading, how it is like, and fatigue striations on the fatigue fracture surface. Parameters are fracture life, fatigue strength, fatigue crack growth resistance, Paris exponent, M, fatigue threshold, KTH. So to improve the properties of the material, first we have to look at the materials actually, material assessment, then we can go for improvement of material properties. So we need to understand mechanical aspects first, that is the relationship between the stress and strain, okay, of elastic behavior, elements of theory of plasticity. Then we enter into the metallurgical aspects, that is plastic deformation, dislocation theory, strengthening mechanisms, and fracture. So these are the references. Okay, you can always follow the detail book for all the details. And the introduction, the chapter one is introduction to the mechanical behavior of the materials. That is the subject. So here we'll be talking about introduction to mechanical metallurgy, strength of materials, basic assumptions, elastic and plastic behavior, average stress and strain, tensile deformation of ductile metals, ductile versus brittle behavior, what constitutes failure, concept of stress and type of stresses and unit of stress and other quantities. So this chapter, it provides a background of continuum description of stress and strain and extends it to the defect mechanism of flow and fracture details. Elastic and plastic behavior of the metals are highlighted, and fracture influencing fracture failure in metals are finally addressed in this chapter. So here in this chapter, we'll be considering the material or the body as a continuum body. Okay, it's a homogeneous body without any heterogeneous stuffs there, but actually the metal is heterogeneous. But here for simplicity we'll be considering a solid continuum. So mechanical metallurgy, as you know, it's a response of metals to forces or load. When you apply force or load on a body, the response to that load is what is the study of this mechanical metallurgy or deformation behavior, whatever you say it as. So mechanical assessment of materials. One is a mechanical assessment of material, that is structural materials, machine, aircraft, ship, car, etc. We need to know limiting values of which materials in service can withstand without failure. Then forming of metals into useful shapes, that is forging, rolling, extrusion, drawing, machining, etc. So here we need to know conditions of load and temperature to minimize the forces that are needed to deform metal without failure. So first is the strength of materials. So strength of materials deals with the relationship between internal resisting forces, deformation, external loads, which act on some part of the body in equilibrium. So you see that in equilibrium condition, if there are the external forces acting on the member, so you see that the green one in the figure over here, the P is the load that is being applied, that is the external force, and there will be always internal forces resisting the action of the external load. You see the internal force, it is nothing but the internal resisting force are nothing but the stress acting over a certain area. This internal resisting force is a stress acting over a certain area, so that the internal force is the integral of the stress times the differential area over which it acts. So P is equal to integral of sigma dA, that is stress times the differential area. Integral of the stress times the differential area is the internal resisting force, which is equivalent to that of the load that is applied. So the concept is that when external load is applied on a member, there is always some internal resisting forces acting on the external loads. And the internal resisting force is integral of stress times the differential area over which it acts. So some assumptions we make in strength of materials is that the body or the member we consider is to be continuous, that is it has no voids or empty spaces, homogeneous, it has identical properties at all points, isotropic, similar properties in all direction orientation. And in macroscopic scale, if you look at engineering materials such as steel, cast iron, aluminum seems to be continuous, homogeneous and isotropic. But in a microscopic scale, Metals are made up of different grains, made up of aggregate of crystal grains having different properties in different crystallographic directions. But these crystal grains are very small, and therefore the properties are homogeneous in a macroscopic scale. Okay, so elastic and plastic behaviors. This we all know in our previous background, as we are all metallurgists. So you see the stress strain curve over here. The solid materials can be deformed when subjected to external load. In elastic region, we all know that if you see the elastic region over here, you'll all know that this elastic region, if you see this elastic region, I know that the stress is proportional to the strain. That is, it obeys the Hooke's law up to the elastic limit. The material now has elastic behavior. At the elastic limit, when the load is removed, the material will change back to its original shape. Beyond the elastic limit, if you see, material gets permanently deformed, or the material has undergone plastic deformation. That means beyond the elastic limit, there is a transformation of the material from the elastic regime of deformation to the plastic regime of deformation. Okay, so this is a load extension curve under uniaxial tensile loading. Okay, so one thing to note here is that the elastic deformation in metals are relatively small in comparison to plastic deformation. Okay, so average stress and average strain. Okay, so if you look at this this cylinder which is attached to a member like this. Okay, one end is fixed and one end is open, and you have a gauge length, that is L0, that is original gauge length, a uniform cylindrical bar which is subjected to an axial tensile load P. The original gauge length L0 has undergone a slight increase in length to L0 plus. So if you're applying a load in this direction, right, this in the axial direction, in axial direction like this P, so the rod or the cylindrical rod bar, it gets elongated. Okay, now previous it was used to be L0, and after elongation you have a different gauge length, that is some L0 plus some delta with a slight decrease in the diameter, of course. Then you can calculate the average elastic strain as the ratio of the change in length to original length. We all know this, that is the final minus the original divided by the original. And regarding the stress, the external load is balanced by the internal resisting force, as we discussed in the previous slide, giving the equilibrium equation P is equal to integral of sigma dA. If you consider that stress is uniform over the area A, then stress can be considered as constant. Then you can take out stress, you have integral of dA, that is sigma dA, that is called your average stress, is sigma by P by A. But here we have considered that stress is uniform over the area, but actually this doesn't happen. At every point stress varies over the area. Okay, so for calculating the average stress, that's why we calling it here average stress, not the stress. This sigma is equal to P by A is not the stress. Load by area is not the stress. It's the average stress. So why are telling it as average stress is that we have considered stress is uniform over the area. Okay. But actually the stress is never uniform over the area. At each point the stress will vary. Okay, so we'll continue with this average stress and strain. In general, the stress is not uniform over the area, as I said in the previous slide. So that's why you're considering it as the average stress. So on a microscopic scale, if you look at metals consists of more than one phase, and therefore they at different phase you will have different, you know this stress values. So that is a non-uniformity of the stress. So below the elastic limit, Hooke's law can be applied, so that average stress is proportional to average strain. So sigma by epsilon is equal to E is what is the modulus velocity of the Young's modulus. Very important property. And this is the stress strain diagram, as you can see over here. This is the stress strain diagram. Okay, this is the stress strain diagram over here, and this is the elastic limit. This is the maximum tensile strain the material can withstand, and then this is the point of fracture. So again, the same thing, the elastic deformation of ductile metal. So in tension test, specimen is subjected to axial tensile load until fracture. Load and extension are measured and expressed as stress and strain. The linear portion of the curve, that is OA over here, if you can see OA is the elastic region where stress is directly proportional to strain, or that is the Hooke's law is obeyed. Point A is the elastic limit, that is the greatest stress that the metal can withstand without undergoing permanent or plastic deformation. and A dash is a proportional limit where the curve actually deviates from linearity, and A is the elastic limit. That is, the elastic limit means the maximum stress or the greatest stress that the metal can withstand without undergoing plastic deformation, and A dash is just above A, which is called the proportional limit, which is nothing but when the curve deviates from the at the point at which the curve deviates from linearity. The slope of the linear portion is the, as you can say, is the modulus of velocity. Point B here, if you can see the green one, the point B over here is nothing but your yield strength. So it is defined as a stress which will produce a small amount of equal strength, 0.002 offset strength. So if you draw a parallel line to the elastic regime at 0.002 offset strength, you will get the line from here, 0.002 offset strength. Parallel line you draw from here, and the line where it cuts the stress strain curve, the point B, is called the yield strength. So as the plastic deformation increases, the metal becomes stronger, strain hardening occurs until reaching the maximum load, giving the ultimate tensile strength D. Beyond D, metal necking forms, that is a reduced in the section. Load needed to continue deformation drops off till failure, and then fracture occurs. As you can see, the different stages of deformation, and it has been shown in the stress strain curve, different stages of deformation. So ductile and brittle behavior. Okay, so completely brittle materials, that is ceramics, as you know, they fracture almost at the elastic limit. So for example, this red one, you can see this is a chest and curve for a ceramic which is completely brittle. It's only you have the elastic region, no plastic deformation whatsoever. And brittle metals as a cast iron, so small amounts of plasticity. You see slightly brittle with small amount of ductility over here. And for engineering materials, adequate ductility is important, as we know, because it allows the materials to redistribute localized stresses. So fracture behavior of metal, ductile or brittle, also depend on some condition, that is temperature, tension or compression, state of stress, strain rate, and all those things we'll see in the different other classes. Okay. So what constitutes failure actually? Okay, so three general ways that cause failure in structural members and machine elements is, one is your excessive elastic deformation, excessive plastic deformation or yielding, and then you have the fracture. Okay, so for a good structural components in service, if you want to develop a good component that can be used in service condition without failure, you need to look at three things: what are the types of load or forces that it is being exposed to, and the nature of material that you are using in that, and the design of that particular material. So these three are critical stuffs that you can look at for selecting a good structural component that can be used in service without failure. Okay, so excessive elastic deformation. Okay, so failure due to excessive elastic deformation, they can be controlled by the modulus of elasticity, not the strength of the materials. Okay, two general types of excessive elastic deformation if you see: excessive elastic deformation under condition of stable equilibrium. Too much deflection in a shaft can cause wear in bearing and damage other parts. And excessive elastic deformation under condition of unstable equilibrium. Sudden deflection or buckling of a slender column. Okay. And then excessive plastic deformation. Excessive plastic deformation occurs when the elastic limit is exceeded. That means yielding, when the material yields. Yielding produces permanent damage of shape, and change can cause fracture. So when component changes in shape, it cannot function properly any longer. So failure of high excessive plastic deformation is controlled by the yield strength of the material. Even in more complex loading condition, yield strength is still a significant parameter. Okay. So metal fails by fracture in three general ways. It can be sudden brittle fracture. Some ductile metal, such as plain carbon steel, will undergo ductile to brittle transitions with decreasing temperature, increasing rate of loading, and triaxial state of stress. Then fatigue or progressive fracture. Most fracture in machine parts are due to fatigue, mainly due to the alternating stress or cyclic loading. The failure is due to localized tensile stress at spot or notch or stress concentration. Then you have delayed fracture, stress rupture failure, which occurs when a metal has been statistically loaded at an elevated temperature. Again, so another concept is the working stress. So what is working stress? To prevent structural members or the machine elements from failure, such members should be used on the stress level that is lower than the yield stress. Because if you are exceeding the yield stress, then there is problem. The fracture can occur immediately, or it is vulnerable for to shape change and deformation. So it has to be worked at a stress lower than the yield stress. Yield stress here we are considering as sigma 0. The stress level is called the working stress, sigma W. So according to American Society of Mechanical Engineering, ASME, the working stress sigma W can be considered as either the yield strength, or it can be considered as a tensile strength divided by safety factor. For example, if you consider working stress in terms of the yield stress, you have N0 sigma 0 by N0, where N0 is safety factor based on yield strength, and for this ultimate tensile strength, you have Nu, which is a safety factor based on tensile strength. Okay, so safety factor depends on loading or service condition, etc. So today we'll stop here, and I think in the next class we'll continue with this. Thank you.